Hello, everyone. Welcome to Sleep Space. Tonight, we'll talk about what's inside a black hole. Where do you go when you fall into a black hole? What happens to matter, to energy, to time, to space itself? Does it all just disappear? Or does it go somewhere else? A place we don't yet understand. Black holes are perhaps the strangest, most extreme objects in the known universe. They defy intuition, bend reality, and challenge everything we know about physics. Yet, despite how mysterious they are, we actually know a great deal about what surrounds them, and we have some remarkable clues about what may lie inside. So, tonight, let's begin at the edge of the mystery, with the surface of a black hole. Not a solid surface like a planet or a star, but something much stranger. It's called the event horizon. The event horizon is not a thing, it's a boundary, a point of no return. If you cross it, you can never escape, not even if you travel at the speed of light. It's like falling off a cliff that has no bottom. Once something goes past this boundary, it disappears from our universe. The term event horizon is powerful for a reason. It means that beyond this boundary, no event, no light, no sound, no signal can ever be seen again from the outside. It becomes silent, forever cut off from the rest of the cosmos. And yet, the strange thing is that the event horizon isn't a wall or a force field. If you fell into a massive black hole, you might not even notice when you cross the boundary. You would just keep falling, gently at first. No flashes, no noise, no sudden jolt. Just darkness, pulling you deeper. But before we fall inside, let's understand how black holes come to be. Most black holes are born from the deaths of massive stars. A star spends its life in balance, gravity pulling inward, and fusion pushing outward. But when the fuel runs out, fusion stops. Gravity wins. The star collapses in on itself. If it's massive enough, the collapse doesn't stop. It keeps going, compressing matter into a smaller and smaller space until it becomes infinitely dense. That's a black hole. More precisely, at the heart of a black hole, we believe there is something called a singularity, a point of infinite density and zero volume, where the laws of physics as we know them break down. It's not that our understanding is incomplete, it's that space and time themselves no longer behave the way we expect. Everything falls toward the singularity. It's the ultimate destination, but getting there is not so simple. To understand the inside of a black hole, we first have to abandon our everyday understanding of space and time. Inside the event horizon, the directions of space and time flip. What was once a direction you could move in, forward, backward, left, right, becomes inescapable like time. It's not just that you can't escape, it's that escape becomes as impossible as moving backward in time. Imagine that instead of falling toward a place, you're falling toward a moment you cannot avoid. That's the pull of the singularity. Even light cannot escape this fate. In fact, the very speed of light, the universal speed limit, becomes meaningless inside the horizon. All paths, whether you crawl, run, or shine a beam of light, lead to the singularity. You don't fall toward it, you're carried, like a river current carrying everything toward a waterfall. There is no swimming back upstream. The geometry of space-time simply doesn't allow it. So what does the inside of a black hole actually look like? That's the difficult part. No one has seen inside and no information can get back out. But based on general relativity, Einstein's theory of gravity, we can model what happens. As you cross the event horizon, you enter a region where space becomes curved to an unimaginable degree. Time begins to distort. To someone outside, you would appear to freeze at the edge. To you, time would seem to pass normally, but you'd be pulled inward faster and faster. The tidal forces, the stretching caused by gravity, would become stronger the closer you get to the singularity. If the black hole is small, those forces would rip you apart long before you get close. Your head and feet would feel gravity so differently, they'd stretch you into a long, thin strand, a process scientists jokingly call spaghettification. But in a supermassive black hole, like the ones at the centers of galaxies, that process happens much deeper inside. You might pass the event horizon and feel nothing. You might drift in silence, but eventually the singularity awaits. Now, here's where things get very strange. According to general relativity, the singularity is a point of infinite curvature. But physics doesn't like infinities. They're usually signs that a theory is breaking down. And here, relativity clashes with another foundational theory, quantum mechanics. Quantum theory tells us that information about particles, energy, and matter cannot be destroyed. But if everything that falls into a black hole is lost, isn't that a kind of destruction? This leads us to one of the greatest puzzles in modern science, the black hole information paradox. It asks a deceptively simple question. What happens to the information that falls into a black hole? If it disappears, we break the rules of quantum mechanics. If it doesn't disappear, where does it go? Some theories suggest the information is somehow stored on the surface, the event horizon itself, and coded in quantum fluctuations. Others propose that black holes evaporate over time, slowly releasing radiation, called Hawking radiation, that carries away the information in a highly scrambled form. But this leads to more questions than answers. We still don't know how to fully reconcile gravity and quantum mechanics. Inside the black hole lies the battleground of the two greatest theories in physics, and we have yet to find the peace treaty that unites them. Yet even though we can't see inside a black hole, we've learned a great deal from the outside. By watching how stars orbit an invisible center, we've discovered supermassive black holes billions of times more massive than our Sun. By measuring gravitational waves, ripples in space-time caused by black hole collisions, we've confirmed their existence in exquisite detail. And in 2018, we saw the first image of a black hole's shadow, captured by the Event Horizon Telescope. It wasn't a picture of the black hole itself, but of the glowing ring of matter swirling around it, matter heated to incredible temperatures just before it disappears forever. That glowing ring, the accretion disk, may be our closest view of what it means to fall into a black hole. It's not just a place, it's a journey, a one-way trip into the deepest secrets of the cosmos. And the more we learn about black holes, the more they challenge what we think we know. They may be portals to other regions of space-time. They may hold clues to the origin of the universe. Some theories even propose that the Big Bang itself was the explosion of a white hole, the reverse of a black hole, spewing matter out instead of pulling it in. Could the inside of a black hole be the seed of a new universe? That's one of the most fascinating possibilities we'll explore as we go deeper, not just deeper into black holes, but deeper into our understanding of the very fabric of reality. Now, as you settle into rest, let your thoughts drift into that darkness. Not a fearful darkness, but a curious one, a place of mystery and wonder. We may not be able to escape a black hole, but we can imagine it, map it, model it. And one day we may even find the theory that finally explains what truly lies within. When we talk about a black hole, We are not simply talking about a hole in space, we're talking about a region of extreme curvature, where gravity is so intense, it changes the very shape of space and the flow of time itself. To understand what's happening inside, we need to understand how gravity really works, especially in extreme cases like this. According to Newton, gravity is a force between two masses, but Einstein saw something deeper. In general relativity, gravity isn't a force pulling things together. It's the bending of space-time itself. Objects like planets and stars create curves in the fabric of space and time, and other objects move through those curves, much like marbles rolling on a stretched rubber sheet. But a black hole doesn't just curve space, it tears it open. It creates what's called a gravity well, so deep, nothing can escape. If you were to fall into this well, the laws of geometry themselves would change. And this isn't a metaphor, it's literal geometry. Distances, durations, and even cause and effect begin to blur. Let's visualize this. Imagine space-time as a flat, stretched membrane. A small mass creates a little dimple. A massive star makes a deeper dent. But a black hole creates a steep, bottomless pit. At the center is the singularity, the point where the curvature becomes infinite. It's the end of the line, the center of the well, and possibly the end of space-time as we know it. Now, this warping has some strange effects. As you approach the event horizon from the outside, time appears to slow down. To an observer watching from a safe distance, you would seem to freeze just at the edge. Your image would grow dimmer and redder, stretched by the extreme gravity until it faded away entirely. But from your perspective, the person falling in, time feels normal. You don't feel any sudden stop. You keep falling. This leads to an unsettling thought. Time inside a black hole is not the same as time outside. In fact, they're not just different. They're oriented differently. Once you pass the event horizon, going forward in space means moving deeper into the black hole. But deeper, in this case, is a direction in time. You can't avoid moving forward in time, and inside the black hole, forward in time means moving toward the singularity. You're not pulled, you're carried by the geometry itself. This shift, where space becomes time and time becomes space, is one of the most mind-bending predictions of general relativity, and it has real consequences. If you could somehow hover just above the event horizon and then drop something, a light, a signal, even just a particle, it would fall inward. Not because it's being forced, but because there's nowhere else to go. It's like rolling a ball down a hill. The hill is not forcing the ball, the geometry of the hill simply directs its path. But we run into problems when we try to take this too far. Remember, general relativity describes gravity and large-scale curvature beautifully, but it says nothing about the quantum world, the world of tiny particles, forces, and probabilities. At the singularity, the density becomes so extreme, we can't ignore quantum effects anymore. And yet, we don't yet have a quantum theory of gravity. This means the very center of a black hole remains an unsolved riddle. It's a place where our current understanding ends. What we do know is this: as matter collapses toward the center, it loses all its previous structure. A mountain, a star, even a spacecraft, all of it becomes part of the black hole's mass. But strangely, black holes seem to be incredibly simple, at least from the outside. They can be fully described by just three properties: mass, spin, and charge. This is known as the no-hair theorem. It means black holes have no hair. No distinguishing features like shape, color, composition, or texture. Just those three quantities. It doesn't matter what falls in. It could be a book, a planet, or a beam of light. Once inside, it adds to the black hole's mass, and any other information is lost to the outside world. Or is it? Stephen Hawking made a groundbreaking discovery in the 1970s that turned this idea on its head. He showed that black holes aren't completely black. They emit a faint glow, now known as Hawking radiation, due to quantum effects at the edge of the event horizon. This means black holes can slowly lose mass over time and eventually evaporate. But if a black hole disappears, what happens to all the information that fell in? This is the heart of the black hole information paradox. According to quantum theory, information can never be destroyed, not even in a black hole. But if the black hole evaporates, where does the information go? Some physicists believe the information is encoded in the Hawking radiation, albeit in a highly scrambled way. Others think it might remain in a remnant, a tiny leftover piece that stores all the data. Still others propose that our entire understanding of space-time needs to be revised, that information might be preserved on the boundary of the universe itself, in a kind of cosmic hologram. The idea of a holographic universe may sound far-fetched, but it's backed by serious mathematical models. In a hologram, a three-dimensional image is encoded on a two-dimensional surface. Some physicists believe our three-dimensional universe might actually be a kind of projection, a higher dimensional phenomenon encoded on the boundary of space-time. If so, then everything that falls into a black hole might actually be stored, not inside, but on the surface. Not lost, just transformed. This leads us into fascinating territory, because if black holes are storage devices for information, cosmic libraries of everything that has ever fallen in, then perhaps they aren't just dead ends. Perhaps they're active participants in the story of the universe. Let's take a moment to return to the experience of falling in. If you were to fall into a black hole, especially a supermassive one, the journey might be eerily quiet. There would be no solid surface to crash into, no sudden halt, just a continuous, accelerating fall into deeper curvature. You wouldn't be crushed immediately. You might have time, seconds, maybe minutes, to think, to observe, to feel the strangeness of existence warping around you. But make no mistake, the singularity awaits. Whether it is a point, a ring, a portal, or something else entirely, it is the place where space and time collapse. What lies beyond? Is there a beyond, or is it the absolute end? This is where speculation meets science. Some theoretical models, like those based on string theory or loop quantum gravity, suggest that the singularity might not be a true point, but a transformation, a kind of bounce where matter is compressed to a minimum size and then rebounds. Could the inside of a black hole be the seed of another universe? It's a provocative idea. In fact, some cosmologists suggest that every black hole might birth a new universe on the other side. If that's true, then our own universe may have formed from the interior of a black hole in some parent universe. This is called the black hole cosmology hypothesis. It's far from proven, but it's mathematically plausible. And if true, it means that the inside of a black hole might not be the end of the story, but the beginning of a new one. Even in their mystery, black holes give us something extraordinary. They teach us the limits of knowledge. They show us where our current theories collide. And they offer a laboratory, a cosmic testing ground for new ideas that may one day unlock the deepest truths of the universe. So, as you float deeper into this quiet darkness, remember, even in the places where light cannot escape, imagination can. Science can. Wonder can. And sometimes the questions are more powerful than the answers. To understand what's inside a black hole, we need to approach it like explorers mapping an invisible world. We can't see the inside directly, and we can't send a probe in and receive data back. But what we can do is use the tools of physics, mathematics, observation, and imagination to build a model of what might be happening within. Let's return for a moment to the event horizon. This is not a wall, but a one-way surface. It's the line you cross and never return from. And although you can't see what lies beyond, the behavior of the event horizon gives us clues. For instance, when a black hole gains mass by consuming stars, gas, or other black holes, the event horizon grows. This tells us that the boundary is not fixed. It shifts and stretches depending on what falls in. And that might tell us something about what's inside, a kind of growing interior, capable of containing vast amounts of matter and energy. Now, let's go a little deeper. Just beneath the event horizon lies what's known as the ergosphere, at least for rotating black holes. Most black holes aren't stationary. They spin, often rapidly, due to the conservation of angular momentum. This rotation drags space-time itself around with it, a phenomenon called frame dragging. In the ergosphere, space isn't just curved, it's moving. If you were there, you couldn't remain still even if you wanted to. You'd be pulled along, forced to rotate with the black hole. This rotation creates opportunities. Theoretically, you could extract energy from a rotating black hole, not by going inside, but by dipping into the edge of the ergosphere and bouncing back out. This is called the Penrose process, and it's more than just a thought experiment. It has inspired real speculation about future energy extraction and interstellar travel. But what's more intriguing is what it reveals about the interior, that it's dynamic, layered, and not a simple void. Beyond the ergosphere and deeper inside, you're pulled toward the core. In a non-rotating black hole, general relativity says you'll reach the singularity in a finite amount of time. That singularity, remember, is a point, infinitely dense, infinitely small, and utterly destructive. But rotating black holes, described by the Kerr solution to Einstein's equations, are different. Instead of a point singularity, the Kerr black hole contains a ring singularity. And mathematically, this changes everything. It means, at least in theory, there might be a path through the singularity, a region where space-time is still well defined. In some solutions, this leads to a white hole, a hypothetical object that does the opposite of a black hole. Nothing can enter a white hole, and everything is expelled from it. In other words, it's a one-way exit. Even more intriguing, some models link black holes and white holes with wormholes, tunnels through space-time. These tunnels, if they exist, could connect distant regions of space, or even distant universes. They might allow a traveler to fall into a black hole and emerge somewhere else, sometime else, or into another universe entirely. Now, this is deep speculation. There's no experimental evidence for white holes or traversable wormholes, but mathematically the solutions exist. And in a universe governed by equations, math is often the first step toward discovery. What these ideas reveal is that black holes might not be endpoints. They could be gateways. But let's return to a more grounded question. What happens to matter inside a black hole? When an object falls into a black hole, it becomes part of its mass, its energy, its rotation. Its original structure is destroyed. Atoms are ripped apart, molecules are crushed, and even nuclei are broken down. But where does it go? One idea is that it becomes part of a mass energy distribution, a dense, compressed layer inside the event horizon. This isn't a core or a crust, but a continuous inward spiral. Time and space become so twisted that all motion leads inward, and the deeper you go, the more extreme the conditions become. Density rises, pressure skyrockets, temperatures climb beyond imagination. At some point, gravity is so strong that even quantum fluctuations, tiny, random changes in energy, become significant. Space-time may begin to foam, boiling at the Planck scale, the smallest unit of distance we can meaningfully define. At this level, smooth geometry breaks down, and quantum gravity is required to describe what happens. But here's the catch. We don't yet have a working theory of quantum gravity. String theory offers one possibility. It says that the fundamental building blocks of reality are not particles, but tiny vibrating strings of energy. Under string theory, the singularity might be avoided because strings cannot be compressed into a true point. Instead, the core of a black hole might be a dense knot of vibrating strings, where space and time are quantized and finite. Another theory, loop quantum gravity, suggests that space-time itself is made of tiny loops, like a woven fabric. In this view, the collapse of matter inside a black hole doesn't lead to a singularity, but to a bounce, a moment when contraction turns into expansion. This might explain the origin of new universes, tiny bubbles of space-time branching off from black holes, each with its own laws of physics. It's not just a poetic idea, it's a serious scientific proposal, explored in leading journals and by top physicists. If true, it means every black hole is not just a grave, it's a womb. Let's pause here and imagine what it might feel like at the edge of such transformation. You are falling deeper, the horizon is long behind you. The light from the outside universe is a faded memory, dim and red-shifted into nothing. Around you, space stretches like taffy. Distances lose their meaning. Objects ahead of you seem unreachable, yet also right next to you. Time feels strange, slower, faster, maybe both. The singularity is not a place, but a moment, and you are approaching it. If your black hole is rotating, you might be spiraling inward, not straight down, but in a helix, circling ever closer, faster, as you approach the ring singularity. Gravity isn't just pulling you, it's twisting you, and all along the way, the very coordinates of space are changing. Down is no longer down. Forward becomes inward. Inward becomes inevitable. What awaits you there? The honest answer, we don't know. It could be oblivion, the annihilation of matter and information, or it could be transformation, the birth of new structures, new rules, a new kind of space. What's so remarkable is that black holes don't just ask us to understand new physics. They ask us to rethink what physics is. They force us to confront the limits of determinism, of observation, of knowledge itself. Can you measure something that cannot send information? Can you describe a region you cannot enter and return from? Can you trust equations beyond the point where the theories that built them fall apart? This is the frontier. And while we may not be able to visit a black hole, we can simulate them. Supercomputers today can model the collapse of stars, the warping of light, and the behavior of matter spiraling inward. These simulations have shown us how jets of plasma shoot out from near the event horizon, how accretion disks form and glow, and how the gravitational pull of a black hole distorts the very image of the space around it. These aren't guesses, they're tests of physics. And so far, the universe has agreed with them. In fact, every time we observe black holes, through telescopes, X-ray data, gravitational waves, we see confirmations. They really exist, they behave as expected, and yet they hold secrets we cannot reach. Which brings us to one final question for this part. What does a black hole feel like to the universe? It is an anchor, a furnace, a hiding place, a clock, a source of entropy, a test of physics, a link in a chain of creation, a mirror for our ignorance and our potential. Black holes are not just the most mysterious objects in the universe. They are also the most precise tests of our understanding of space, time, and matter. They push our theories to their limits, and beyond those limits, they quietly wait. In that waiting, they reveal. Let's now explore how black holes are used, not physically, but theoretically, as natural laboratories. Because when something breaks the known rules, it forces us to reconsider the foundations. And few things break the rules like black holes. First, we need to return to Einstein. His equations of general relativity are precise, elegant, and incredibly successful. They describe how mass and energy curve space-time, and how that curvature tells matter how to move. These equations predict that if you compress enough mass into a small enough space, the curvature becomes infinite. A singularity forms, and a black hole is born. But Einstein himself was uneasy with this. He didn't believe that nature would allow such infinities. In fact, for years, many physicists thought black holes were just mathematical artifacts, interesting but not real. It wasn't until the 1960s and 70s, through the work of physicists like Roger Penrose and Stephen Hawking, that black holes became accepted as physical reality. Roger Penrose showed that under very general conditions, such as during the collapse of a star, singularities are unavoidable in general relativity. Stephen Hawking extended these ideas to the entire universe, showing that the Big Bang itself may have been a singularity. In doing so, they revealed that black holes are not rare, exotic objects. They are fundamental to the structure of the cosmos. And so we began to ask deeper questions. What can a black hole tell us about the nature of time? What can it reveal about the limits of information? What happens to entropy, the measure of disorder, when matter falls in? Let's take that last question. In classical physics, the second law of thermodynamics says that entropy must increase over time. Systems naturally evolve toward greater disorder, but black holes seem to violate this. When you throw matter into a black hole, you lose track of it. The entropy of the universe appears to decrease. Where does the disorder go? The answer, once again, came from Hawking. In collaboration with Jacob Bekenstein, it was proposed that black holes do have entropy, and that this entropy is proportional to the surface area of the event horizon, not the volume inside. This was an astonishing idea. It means that all the information about what's inside a black hole is somehow stored on the outer surface, not in the depth, but on the edge. This was one of the first hints at something profound, a principle that would later be called the holographic principle. It suggests that the physics of a volume of space can be described by information encoded on a boundary surrounding that space, much like a hologram. Black holes, then, might be telling us that the universe itself works this way. that we are all, in some sense, projections from a deeper layer of reality. This idea has grown far beyond black holes. It's now a major part of theoretical physics, especially in string theory. It leads to models where space and time emerge from networks of information. It suggests that geometry, gravity, even causality itself may be built from something more fundamental: relationships between quantum bits. But let's return to the black hole. If information is stored on the event horizon, then the surface area becomes more than just a measurement. It becomes a kind of book cover, a place where the entire contents are encoded, if only we could read the language. In this view, the interior of a black hole is not really hidden. It's just encrypted. It's there, waiting to be understood, if we can develop the right tools to decode it. And that's exactly what many physicists are trying to do. Quantum field theory, which describes particles and forces, works beautifully in flat space-time. But near a black hole, where curvature is extreme and time itself becomes warped, it starts to break down. We need something better, a way to unite general relativity with quantum mechanics. That's the long-sought goal of quantum gravity. There are many competing theories: string theory, loop quantum gravity, causal dynamical triangulations, and more. All of them try to describe how space-time behaves at the smallest scales, where quantum uncertainty and gravitational collapse meet. And in all of them, black holes are the ultimate proving ground. Because if your theory cannot explain what happens inside a black hole, it cannot be a theory of everything. And so, black holes have become more than just astrophysical objects. They are theoretical filters. They allow only the most consistent ideas to pass. They serve as a forge, burning away the fluff of incomplete concepts, and leaving behind only those that can survive the heat of paradox. Even the idea of space and time themselves has come under question. In many quantum gravity models, space-time is not fundamental. It emerges from something deeper, a kind of quantum entanglement between units of information. If that's true, then the interior of a black hole isn't a place in space. It's a pattern in a sea of probabilities, a knot in a web of entanglement, a page in a book written in a language we don't yet speak. So what are we left with? We are left with an object that behaves like a perfect absorber, an entity that, from the outside, tells you nothing but three facts: mass, spin, and charge. And yet, inside, it may be buzzing with complexity, roiling with information, echoing with the traces of everything that's ever fallen in. And all of this incredible complexity, may be hidden on the surface, as if the inside is not deep but shallow, as if depth itself is an illusion. What does this tell us about reality? It tells us that what we see may not be the whole picture, that space may be emergent, that time may be directional, not absolute, that the division between inside and outside may be more porous than it seems, and that, perhaps, the universe is not made of things, but of information. This is what black holes force us to consider, and still, they are real. These aren't abstract fictions. We have measured their gravitational pull. We have heard their collisions in the form of gravitational waves. We have seen the silhouettes they cast against glowing disks of matter. In 2015, the LIGO Observatory detected the collision of two black holes. That moment, a tiny tremor in space-time, barely noticeable, confirmed Einstein's prediction from a century earlier. And it told us that black holes don't just sit quietly. They move, they merge, they grow, they dance, and when they do, they shake the universe. The waves they produce, gravitational waves, pass through everything, warping space itself. These waves carry with them a signature: the mass of the black holes, their spin, the moment of merger. From these patterns, we can reconstruct the event. We can hear, in the tremor of space-time, the story of something that happened billions of years ago. And so we return, once again, to the edge of a black hole. We stand at the event horizon, not as passengers, but as scientists, dreamers, explorers. We stare into the dark, not with fear, but with questions, with curiosity, with awe. Because the inside of a black hole is not just a location, it is a mystery that reflects our own desire to understand, to know, to unify the forces of nature, to reach beyond the boundary, and maybe, just maybe, to understand ourselves. Imagine, for a moment, that you are a single photon, a tiny particle of light, drifting through space. You've traveled across the cosmos for billions of years, passing stars and dust and interstellar silence. But now, your path curves sharply. A black hole has pulled you in. You try to resist, but resistance means nothing here. Gravity isn't a force anymore. It's the shape of the space you're moving through. Your future has been bent inward. You reach the event horizon and you do not stop. From your perspective, the journey continues. But for anyone watching from far away, you've disappeared. Your image lingers, stretched and red-shifted, until it fades completely. You're gone, not just from view, but from the entire observable universe. That's what happens to all matter and energy that cross the horizon. It becomes unobservable. But unobservable doesn't mean non-existent. The laws of physics still apply inside, or at least they try to. Matter continues to move. Energy continues to flow. And space-time continues to bend. The question is, bend into what? Let's follow a different traveler. A spacecraft, for example, designed to withstand the immense gravitational gradients inside a supermassive black hole. Unlike a small black hole, where tidal forces would destroy the craft almost instantly, the interior of a supermassive black hole might allow the ship to survive long enough for detailed observation. Time passes normally inside. The crew watches their instruments, trying to make sense of the unfolding geometry. They might see strange things. Light from the outside universe would become increasingly redshifted, lower in frequency, slower, dimmer. Eventually, the stars would vanish entirely, leaving only blackness. Not because the stars are gone, but because their light can no longer reach you. You're inside now. Time itself flows inward. If you looked around, your visual field might warp. Light curves around you in spirals, bent by extreme gravity. Forward becomes downward. Directions lose their classical meaning. In the far distance, or rather the inevitable future, is the singularity. As we mentioned before, in a rotating black hole, this singularity isn't a point. It's a ring, a one-dimensional loop of infinite density. In the equations, this ring allows for a hypothetical passage into a new region of space-time. Mathematically, there's a path through it, a kind of tunnel that might emerge elsewhere. But this is only a feature of the equations. Whether it's physical is unknown. Still, the idea persists. Could something fall into a black hole and exit through another universe? Could we send information through? Could a black hole be a kind of one-way door, or even a two-way portal? Physicists call these hypothetical paths wormholes. They appear in solutions to Einstein's equations, but keeping them stable seems impossible without exotic matter. matter with negative energy density. We've never seen such matter in nature, but quantum theory doesn't rule it out entirely. If it could exist, perhaps wormholes could stay open, perhaps information could pass through safely, and yet the black hole fights back. The more you try to force information through, the more unstable the geometry becomes. Any attempt to keep a wormhole open causes it to collapse, crushed by its own gravity. It seems the universe guards its secrets carefully. Even so, some theories propose that wormholes could exist inside black holes, briefly, at the moment of formation. These are called Einstein-Rosen bridges, and they connect two black holes through a shared interior. If you could enter quickly enough and survive the forces inside, you might pass through the bridge before it collapses. But this is speculation. Still, speculation has value. It tells us where the edges of our knowledge lie. Now let's ask a different question. If information enters a black hole and is somehow preserved, whether on the surface or in radiation or through holographic encoding, then what happens when the black hole evaporates? Stephen Hawking's theory of black hole evaporation says that black holes are not eternal. They radiate slowly, losing mass over time. This process takes unimaginable durations for stellar or supermassive black holes, longer than the current age of the universe. But eventually, they shrink. As they lose mass, they radiate faster. In their final moments, the radiation surges. Then, silence. So what's left? Does the black hole vanish completely, or is there a remnant, a last speck of concentrated information, smaller than an atom, heavier than a mountain? Some theories suggest such remnants may exist. Others argue that all the information must have already escaped in the radiation. But how? Radiation is random. Hawking radiation, in its original form, carried no information. And that's the paradox. To resolve it, physicists have explored new models. Some say the outgoing radiation becomes entangled with the interior, slowly transferring the encoded information outward. Others propose that black holes are more like scramblers, systems that mix up the data and then emit it in a complex, encrypted pattern. Over time, the pattern reveals everything that went in reverse. This idea, called unitarity, is central to quantum theory. It says that information is never lost, only transformed. And if it's true for black holes, it must be true for everything. Even destruction is reversible, at least in principle. But to accept this, we have to let go of certain intuitions. We have to stop thinking of black holes as objects and start thinking of them as processes, as dynamic systems, as bridges between what we know and what we don't. And in that space, the space of not knowing, something remarkable happens. Physics stops being about certainty and becomes about possibility. Let's go back one last time to the experience of falling in. You are drifting inward, past the horizon, through the warping light, into the dark. There is no sensation of crossing. There is no resistance, just a slow surrender to the shape of space. Around you, there is silence. Ahead of you, time has become direction. You are not falling through space. You are falling through time, and all paths lead to the same destination. But what if the destination is not the end? What if, at the moment of ultimate compression, at the moment when space-time can no longer shrink, something new emerges? A bounce, a transition, a rebirth. In loop quantum gravity, this is not just an idea, it's a prediction. The core of the black hole, instead of collapsing into nothing, reaches a minimal volume. a quantum of space, and then expands again. But not in our universe, in a new one. If true, this means every black hole could be a seed, and inside every seed, every singularity, could be the spark of a new cosmos. New space, new time, new laws. And if this is true, then we may be part of a cosmic lineage, one universe birthing another through black holes in a chain that stretches backward forever. Universes giving rise to universes, each one contained in some unfathomable way within the other. This doesn't mean we'll ever travel to those places, but it means something even more profound. It means that our universe may carry the imprint of others, that the very structure of reality, the constants of nature, the form of galaxies, the fabric of space, may be shaped by what came before. And so the inside of a black hole is not just a question of where, it's a question of why. Why does matter fall inward? Why does information scramble? Why does entropy grow? Why does time have a direction? Why does anything exist at all? Black holes contain no light, but they reflect every one of these questions back to us. In their silence, they echo the deepest mysteries of existence. And in that echo, we find not fear, but wonder. Imagine space itself as a flexible, stretchable fabric. Every object with mass rests on this fabric, curving it slightly. A planet, a star, even your own body. But a black hole doesn't just rest on space. It punches a deep, nearly bottomless well into it. The depth of that well depends on the black hole's mass, but its most dramatic feature is the sharp boundary we've already crossed, the event horizon. Now that we're inside, things get even stranger. There are no solid surfaces here. The interior of a black hole is not a place with walls, floors, or even familiar shapes. It's more accurate to think of it as a region where time and space exchange roles. Outside a black hole, you can move freely in space, and time ticks forward predictably. But once inside, space becomes constricted and singular, and time rushes you forward, toward the singularity, whether you want to or not. You're not just falling into a black hole, you're moving forward in time, and that time has only one destination: the center. So what happens to the structure of matter inside? What happens to the atoms, the particles, the fields? Let's consider a human-scale object, say, a probe made of the strongest material we can imagine. As it moves inward, it will encounter tidal forces. These aren't the kind of tides caused by the moon. These are gravitational differences so extreme they can tear molecules apart. In smaller black holes, these tidal forces spike sharply near the horizon, the infamous spaghettification effect. The object gets stretched lengthwise and compressed sideways. But in supermassive black holes, this happens deeper in. The probe could pass the horizon without damage, for a while. As it approaches the singularity, though, everything begins to fall apart. Electrons are stripped from atoms. Atomic nuclei are crushed. Eventually, even the particles themselves may break down. This is where quantum mechanics begins to dominate, and where classical physics fails us completely. According to quantum field theory, every particle is a ripple in an underlying field. Electrons in the electron field, quarks in the quark field, and so on. These fields fill all of space, including the inside of a black hole. But what happens to the structure of these fields as space itself collapses? That's where we enter the frontier of modern physics. One proposal is that near the singularity, quantum fluctuations become so intense that they overwhelm the classical structure of space-time. Instead of a sharp point, The singularity may be a region of chaotic, seething quantum foam, a state where geometry breaks down completely. No coordinates, no dimensions, just pure energy, flickering with possibilities. Another idea comes from string theory, which suggests that all particles are tiny, vibrating strings, each with its own frequency. In this view, the singularity isn't a point at all. Instead, there's a minimum length, the string scale, beyond which no further compression is possible. This natural limit could prevent the formation of an infinite density point, replacing it with a finite, albeit incredibly dense core. Inside, strings may vibrate wildly, interacting through extra dimensions curled up beyond our view. And if those extra dimensions exist, they may become relevant in the extreme conditions of a black hole's interior. Some theories suggest that gravity can spread through these extra dimensions, weakening its apparent strength in our three-dimensional world. But inside a black hole, gravity becomes dominant. Perhaps the very fabric of these hidden dimensions is revealed or torn open. Let's imagine for a moment what it might look like, not visually but mathematically, inside this core. Space-time is no longer smooth. It becomes turbulent, granular, made of quantum bits. Each bit carries a piece of information. Some theories even suggest that space is made of information, that geometry itself emerges from entangled quantum states. If that's true, then the interior of a black hole might not be a place at all. It might be a computation, a dynamic network of data nodes, evolving according to quantum rules. This leads us to one of the most radical ideas in modern physics. ER is EPR. This equation proposes that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen quantum entanglement are the same thing. In other words, two particles that are entangled across space might be connected through a microscopic wormhole. If this is true, then perhaps the interior of a black hole is a vast web of entangled pathways, a place where information isn't lost, just deeply scrambled and rerouted. This could explain how black holes manage to preserve information while seeming to destroy it. Instead of leaking it out gradually or storing it on the horizon, perhaps they entangle it with particles far away, in subtle and intricate ways. Over time, that entanglement could be revealed through the black hole's radiation, not randomly but carefully encoded, like a message slowly emerging from static. But how does this connect with reality? Can we test it? That's where the study of gravitational waves becomes important. When two black holes merge, they release ripples in space-time that travel across the universe. These ripples carry signatures, patterns, of what happened inside. By studying them carefully, scientists hope to infer properties of the interior, how space curved, how energy moved, how singularities collided. Already, observatories like LIGO and Virgo have detected dozens of black hole mergers. In each one, they've seen the final ring down, the moment when the new black hole settles into its final shape. These ring downs tell us about the surface, yes, but they may also hint at deeper processes. For example, if quantum effects are significant near the core, they might cause tiny echoes in the gravitational wave signal, a faint repetition just milliseconds later. Some physicists have looked for these echoes. So far, the evidence is inconclusive, but with more sensitive instruments, the signal could emerge. Imagine the implications: a ripple from a distant galaxy whispering the structure of a singularity. It would be like hearing the shape of an idea, a vibration of the deepest unknown. And if we ever do detect these signatures, They will guide the next generation of theories. They will sharpen our models, clarify the math, and perhaps one day allow us to simulate the interior of a black hole in full detail. That's not science fiction. Quantum computers, in theory, could one day model black holes on a microscopic scale. By encoding space-time geometry into qubits, we might simulate singularities, test entropy flow, and decode the quantum structure of gravity itself. We may never enter a black hole physically, but we might map its interior with perfect accuracy down to the tiniest quantum wiggle. In that sense, black holes are no longer barriers. They're mirrors. They reflect the structure of the universe and of our minds. As we move deeper into this mystery, something becomes clear. Black holes are not just places where things end. They are places where our understanding begins to transform. The familiar laws break down. The known becomes unknowable. And in that boundary lies the essence of discovery. Not because we will conquer the black hole, but because the black hole transforms us. It bends our expectations, it tests our logic, it stretches our models, and in doing so, it forces us to evolve. That is the real interior of a black hole. Not a singularity, but a singular invitation. An invitation to go beyond what we know and to imagine what lies beneath the surface of reality itself. Inside the black hole, the familiar scaffolding of the universe continues to erode. We've passed beyond the realm where classical physics can guide us and entered a space ruled by extremes. Infinite density, warped time, and the breakdown of geometry itself. Yet paradoxically, it's here, deep within these extremes, that we may find answers to the most fundamental questions about reality. At the center of this enigma lies the singularity, not just a place, but a concept that defies conventional meaning. Mathematically, it's where the curvature of space-time becomes infinite, where gravity pulls with unmeasurable force. But no real physicist believes in infinities as actual physical entities. Infinities signal a flaw, not in nature, but in our equations. They are the universe's way of telling us that we don't yet understand. So what could lie at the center instead? One hypothesis suggests a core of quantum gravity. This is not a new kind of matter, but a new kind of space-time, one that behaves differently at the smallest scales. At these Planck scale distances, 10 to 35 meters, space may not be smooth and continuous. Instead, it might be granular, like pixels on a screen, made of discrete units we can't yet observe directly. This quantum space-time might resist total collapse. Instead of forming an infinitely small point, the matter could settle into an ultra-dense but finite region, a kind of quantum cushion where the force of gravity is counterbalanced by quantum repulsion. There are even models that suggest this core could bounce, in a theory known as a black hole to white hole transition. The matter collapsing inward might one day be released, not through an explosion, but through a transformation. The black hole would eventually become a white hole, expelling all the energy it once captured. The process could take billions or even trillions of years from our point of view, but from inside, time may flow differently. This idea arises in loop quantum gravity, a theory that attempts to quantize space itself. In this model, space-time is made of loops woven into a network, a spin foam. Inside a black hole, this network could compress but not break. At some threshold, it might reverse. The collapse halts and expansion begins. It's a bold idea and not yet proven, but it has one compelling feature. It preserves information. This brings us back to one of the most urgent puzzles in physics, the black hole information paradox. According to quantum mechanics, information can never be destroyed. Even if a particle is shredded, merged, and swallowed by a black hole, the information it carried, the quantum state it was in, should still exist in some form. Yet according to Hawking's early work, black holes emit radiation, now known as Hawking radiation, that is entirely random. As the black hole evaporates over time, it seems to leave behind nothing but heat, no data, no memory of what fell in. This contradiction between quantum theory and general relativity has troubled physicists for decades, but several new ideas have emerged that may point toward a resolution. One of the most promising is called the holographic principle. According to this idea, everything that happens inside a volume of space can be described by information encoded on its boundary. In the case of a black hole, that boundary is the event horizon. The 3D interior might actually be a projection, a kind of hologram, emerging from data stored in 2D on the surface. This idea first arose from string theory and was developed further by physicists like Gerard 't Hooft and Leonard Susskind. It was given strong support by the ADS-T correspondence, a mathematical duality discovered by Juan Maldatina in the late 1990s. In this framework, a gravity-based universe in one set of dimensions is exactly equivalent to a quantum field theory in one fewer dimension. So, applied to a black hole, this would mean everything happening inside, the collapse, the stretching, the chaos, is actually a quantum computation playing out on the horizon. There's no inside in the traditional sense. The interior is just another way of reading the same data. If true, this could solve the information paradox. Information isn't destroyed, it's scrambled, preserved on the horizon, and possibly released through subtle patterns in the Hawking radiation. But this raises another question. If the horizon contains the data, does that mean it's physical? Could the surface itself have a microscopic structure? Some theorists have proposed the existence of soft hair on black holes, not literal hair, but low-energy quantum excitations that cling to the horizon. These soft modes could carry the imprint of everything that ever fell into the black hole, like grooves on a record. If we could understand this surface structure fully, we might be able to reconstruct the history of a black hole from its radiation, like reverse engineering a song from vibrations in the air. Even more radical are proposals like the firewall hypothesis. This idea suggests that the horizon might not be smooth and gentle, as general relativity predicts, but searingly hot and violent. An infalling observer, instead of gliding through, would be incinerated upon contact. Firewalls arise from trying to preserve unitarity in quantum mechanics, but they clash with the equivalence principle of general relativity, the idea that free fall should feel like nothing at all. Reconciling these competing truths remains an open challenge, and yet these debates all point to one truth. The interior of a black hole is not empty. It's rich with structure, whether physical, informational, or emergent. It's a place where the known rules compete, clash, and dissolve. A place where we're forced to invent new ways of thinking. Consider this. What if space and time themselves are not fundamental, but emergent? What if they arise from something deeper, something beyond geometry? There are models now suggesting that entanglement, the quantum connection between particles, may be the glue that holds space-time together. That the smoothness of space, the continuity of time, the structure of gravity, all of it, might emerge from vast networks of quantum relationships. In this view, a black hole is not a hole in space, It's a knot in the fabric of entanglement, a place where the threads are wound so tightly that space dissolves, and only the underlying connections remain. And that's the great irony. In trying to look inside a black hole, we may be looking at the foundation of the universe, not a place where things disappear, but where everything begins. Not a void, but a seed, a singularity not of destruction, but of potential. Inside the black hole, we are no longer observing the universe as it is. We're observing what it could be. We're probing the quantum threads that weave the cosmos. And in doing so, we are forced to ask, what is real? What is time? What is existence at its core? Black holes ask these questions silently, not with sound, but with gravity, not with words, but with curvature. And we, slowly, are learning to listen. The idea that reality itself might emerge from something deeper than space and time is more than just a poetic notion. It's a serious proposal at the frontier of physics. And nowhere does that proposal become more urgent than inside a black hole, because here, the usual tools of understanding, the coordinates, the distances, the clocks, all break down. Yet something still exists, something endures. To understand this enduring core, physicists are beginning to explore not just new theories, but new principles. One such principle is complementarity, the idea that different observers may experience reality differently and both be right. Outside the black hole, an observer sees matter slowing down, heating up, and never quite crossing the event horizon. But inside, the matter passes through, seemingly without resistance, toward the singularity. In most areas of physics, conflicting observations like this would spell disaster. But black hole complementarity suggests a compromise. No single observer ever sees both pictures at once. If you're outside, the horizon is the final boundary. If you're falling in, the horizon is just the beginning. There's no contradiction because the laws of physics prevent the two perspectives from comparing notes. This duality hints at something profound, that reality may be observer-dependent, not because of illusion or subjectivity, but because of fundamental quantum limits. This is where quantum mechanics and general relativity start to dance, awkwardly, but in rhythm. And then there's the possibility of wormholes, Einstein-Rosen bridges, emerging inside black holes. Originally proposed in 1935 by Einstein and his colleague Nathan Rosen, these are theoretical tunnels through space-time, connecting distant regions or even separate universes. In the traditional view, wormholes inside black holes collapse too quickly to allow anything to pass through. But recent ideas, especially in the context of quantum entanglement, suggest a connection between these bridges and the mysterious links between particles. This leads to the provocative proposal, ER als EPR. That is, Einstein-Rosen bridges are equivalent to Einstein-Podolsky-Rosen entangled pairs. Wormholes and entanglement, two concepts born decades apart, might be the same phenomenon in different clothing. If true, this means that space-time itself could be woven from quantum entanglement, and the inside of a black hole might contain hidden passageways, not necessarily to other places in space, but to other pieces of information encoded across the universe. These connections would be subtle, invisible, and untraversable in practice, but they could shape the internal geometry in ways we haven't yet imagined. Even more intriguing are the simulations emerging from quantum computing. Using models like ADS-T, physicists have begun constructing simplified black holes on quantum processors. These toy universes, tiny and abstract, still capture key properties of real black holes: event horizons, information scrambling, even evaporation. And they offer a testing ground for theories we could never verify in actual space. Through these digital black holes, we're learning how information might be encoded, preserved, and released. We're seeing how complexity grows inside the horizon and how quantum chaos unfolds. These experiments aren't just metaphors, they're previews of a future in which reality is probed not just with telescopes, but with logic gates. And what of time itself inside a black hole? From the outside, time near the event horizon appears frozen. Light escaping from near the surface is stretched into longer and longer wavelengths until it fades entirely. But for an object falling in, time seems to continue normally, at first. As the gravitational field intensifies, the flow of time becomes distorted. In some interpretations, the singularity lies in the future of every infalling particle, like the end of a movie, inevitable and unchangeable. You don't fall toward it so much as you're carried there by time itself. Others suggest that time, like space, becomes unrecognizable inside, that near the core, the distinction between past, present, and future blurs. There is no before or after, only a complex web of events, curled and folded by the geometry. In this sense, the center of a black hole might resemble the origin of the universe, the Big Bang. Both involve a breakdown of classical space-time. Both are places where density and temperature soar beyond comprehension, and both may require a new theory of quantum gravity to fully explain. This similarity has led some theorists to suggest that every black hole could be the seed of a new universe. That what we call a singularity is not a dead end, but a bridge, a pinch point in the fabric of creation. In such a model, when matter collapses beyond the event horizon, it doesn't vanish. It tunnels through to a new, expanding region, a baby universe, disconnected from ours except through the black hole itself. From the inside, this new universe would appear to begin with a bang. From the outside, we would see only the black hole. This is more than speculation. Certain models of cosmological inflation, the process that rapidly expanded our own universe, can be mapped onto black hole interiors. The equations are eerily similar, and while we don't yet have a way to test this directly, it remains one of the most mind-bending ideas in modern science, that our universe could be the interior of a black hole formed in another. What does this mean for what's inside a black hole? It means the question itself may be incomplete. We're not just asking what's physically located inside, we're asking what rules apply, what kind of geometry exists, whether time flows forward, whether information is preserved, whether this structure is connected to others, whether it's a bridge or a trap, whether it ends in stillness or bursts into something new. Every answer leads to another question. And through it all, there's one truth that persists. Black holes are not just holes in space. They are engines of inquiry. They force us to test the boundaries of knowledge, to unite the smallest scales with the largest, to find harmony between gravity and quantum mechanics, between order and chaos. We used to think of black holes as monsters, cosmic vacuum cleaners devouring everything in their path. But now we see them as laboratories, silent, invisible, yet rich with clues. They're not empty, they're full of possibility, full of tension, full of data, full of connections we don't yet know how to read. And maybe, in the end, what's inside a black hole isn't just matter or energy or space or time. Maybe what's inside is the question itself, the place where physics, philosophy, and imagination converge. The place where the universe hides its secrets, not to keep them from us, but to inspire us to go deeper. We've explored singularities, space-time, information, and even the idea that black holes might birth new universes. But now, let's step back, not away from the mystery, but deeper into it. Because what lies inside a black hole might not just reveal something about astrophysics, it might reveal something fundamental about reality itself. One of the most surprising developments in recent physics is the idea that space might not be fundamental. Instead, it could be emergent, like temperature or pressure or sound. None of those are built into the universe at the smallest scales. They arise from the collective behavior of more basic elements. Physicist Eric Verlinde proposed that gravity, too, is not fundamental, but an emergent phenomenon, a kind of statistical force that arises from information spread across space. And black holes, as concentrated packets of entropy and geometry, are the clearest clues we have to support this idea. If gravity is emergent, then the inside of a black hole is not a place where gravity becomes infinite, but where our current understanding of emergent geometry breaks down. In other words, the singularity isn't a thing, it's a symptom, a signal that the smooth picture of space and time has ended and something else has taken over. This something else could be information, pure quantum bits, entangled and encoded. In this model, space is just a map of how quantum information is arranged. So when you ask what is inside a black hole, you're not asking about a place, you're asking about the structure of entanglement. This is where black hole physics becomes deeply connected to quantum error correction. In quantum computing, information is fragile, easily lost to noise or decoherence. So scientists use error-correcting codes to protect it, even when individual bits fail. Astonishingly, the same kinds of codes appear in the mathematics of black hole interiors. The geometry of space-time itself seems to protect information, even when it's hidden behind an event horizon. This discovery is reshaping how we think about space, not as a backdrop, but as the result of data stitched together by logic and symmetry. So what's inside a black hole? In one sense, it could be the ultimate hard drive, the most sophisticated encoding mechanism in the cosmos. Every particle, every photon, every interaction that fell inside is not gone, but transformed, compressed into a new form, waiting to be released. We don't yet know how that release works, but one possibility is soft hair, a poetic term for subtle quantum imprints left on the event horizon. These imprints may store the information of what has fallen in, like grooves on a record. They're nearly impossible to detect, but theoretically, they allow the black hole to slowly whisper out its contents over eons. And then there's chaos. Not the everyday kind, but quantum chaos. Black holes are now considered some of the fastest scramblers of information in the universe. Drop something in and it becomes entangled with the whole black hole almost instantly. The original pattern is not destroyed, but thoroughly mixed. This scrambling is a clue to how black holes process information. It's not random, it's complex. It obeys rules, and it suggests that even the most extreme parts of the universe operate according to deep order, even if we can't yet see it. Recent work has gone further. Some physicists, like Juan Maldacena, have proposed that the inside of a black hole is actually constructed from the information entangled across the horizon. That is, the interior doesn't exist independently. It is defined by what's outside. This leads to something astonishing, the bulk reconstruction principle. Using mathematical tools from ADS T-duality, it's possible to take data from a quantum system living on the edge of a region and reconstruct what's going on in the bulk, the inside. This is like building a three-dimensional world out of information stored on a two-dimensional screen. So perhaps the inside of a black hole is not a place we need to enter. Perhaps it's a region we can build, using logic, computation, and the rules of entanglement. It's a bit like a hologram. If you shine light through the right pattern, the image appears three-dimensional, but it's all encoded on the surface. Likewise, the 3D interior of a black hole may be a kind of holographic illusion, emerging from the 2D surface of the event horizon. This doesn't make it any less real. The chair you sit on, the air you breathe, they may also be holographic at the deepest level. What black holes give us is a window into how that illusion is built and how it can break. And when you go far enough into the mathematics, something eerie begins to happen. Black holes start to look like quantum computers. They take inputs, matter, energy, information. They process that input through complex transformations, scrambling, entangling, encoding. And then, over unimaginable timescales, they produce outputs. Hawking radiation, fluctuations, ripples in the fabric of space-time. This isn't just a metaphor. Researchers have shown that the entanglement structure of black holes behaves like a computational circuit. That complexity grows inside the black hole, just as it does in a quantum processor. And that the singularity, the apparent endpoint of time, may correspond to a maximum computational limit. Beyond that point, the system can't evolve further without contradiction. It's like a computer reaching the edge of its storage. The laws don't break, they just can't go forward. If all of this is true, then the inside of a black hole is not made of fire or darkness or destruction.
It's made of structure.
An invisible, vibrating, logic-bound maze of quantum rules. A place where time twists, space folds, and information finds new paths. And maybe that's the most beautiful part. Because black holes don't have to be terrifying. They don't have to be the end of understanding. They can be invitations, questions wrapped in geometry, doorways to deeper laws. We may never physically visit the inside of a black hole, but through mathematics, thought, and imagination, we can go there. As we come to the close of our journey inside the black hole, let's pause and reflect on the incredible complexity we've uncovered. From the edge of the event horizon to the deepest mysteries of singularities, from warped space-time to quantum entanglement, we've explored a realm where physics challenges our imagination. Black holes, once thought of as simple voids, reveal themselves as profound laboratories of the universe's most fundamental laws. They stretch our understanding of space and time, challenge how information is preserved, and invite us to rethink what reality truly is. Tonight, as you drift towards sleep, remember that the universe is vast and full of wonders beyond what our senses can perceive. Inside a black hole lies a world where time flows differently, where space folds into itself, and where the very fabric of existence is woven from threads of quantum information. Though we may never journey physically inside a black hole, our minds can travel there freely. The questions it poses about gravity, quantum mechanics, information, and existence are invitations to curiosity and discovery. So as you rest, allow these mysteries to gently unfold in your thoughts. Let the silence of the cosmos calm your mind. Know that in the vastness of space and the depths of black holes, the universe is holding secrets, patiently waiting for us to understand.
Sleep peacefully, knowing you are part of this cosmic story. A story that connects the smallest quantum bit to the grandest galactic swirl.
Thank you for joining me tonight at Sleep Space, where science and wonder come together in quiet harmony. Good night.